All right, let's look at problem set number 1, problem 3. Consider the following investment opportunity. The decision is whether to invest $10 million in a venture. The payout of the venture, if successful, is uncertain. And if the venture succeeds, you will receive $50 million with probability 0.6 and $5 million with probability 0.4. Otherwise, you receive nothing. Assume the probability of success is 50%. So let's draw a decision tree, and let's look at the decision basis. The decision basis are the alternatives, uncertainties, and values of a problem. And for this, similar to problem 2, the alternatives are to either invest or not invest. The uncertainties is actually two of them this time. There is the successful venture or not, which is similar to problem 2. But in addition, there is a payout of the venture is successful. There's uncertainty around that. And then finally, the value is still the same. It's going to be in dollars million, with more is better. So let's go ahead and draw a tree from this, describing this problem. So we have the initial investment. We have a decision, so it's a square. And then emanating from that, or follows from that, are different paths. So one path is the invest path. We're going to invest $10 million. And then if we're going to have uncertainty, and we're either going to be successful, so we'll label that as an S, or we're going to fail. You can see there's almost an art in drawing these things. And then we have the, if successful, what's the outcome of our success? So we have a high value and a low value. The high value was, so our value is dollars million. And the high value is a $50 million payout, but we have to invest $10 million as we go down this path, which results in $40 million. And then likewise down here, we gain $5 million payout, but we lose 10 for the investment, and the result is a minus $5 million outcome to us. If we fail, let's extend this line a little bit, we're going to still lose our $10 million. Still have to spend that, but there's a chance of failing. And the chance of failing was what, 0.5, so probabilities. And once again, since these probabilities have to sum to 1, it's 0.5. The probability of the high valued outcome is 0.6. And we know this has to be 0.4 because it has to be collectively exhaustive, which is a fancy term saying the probabilities have to sum up to 1 for a tree. All right, then the other alternative is the not invest. So this is the not invest branch. And in this case, you're not investing, so it's the do nothing, so it's 0. So this is our decision tree. Once again, it starts with the investment decision, and either you invest or not invest, the two alternatives. If you invest, then it depends if you're successful or fail. If you're successful, there's a chance you could gain $50 million with a 0.6 chance, or $5 million with 0.4 chance. We need to subtract off at the end, our outcomes, our consequences, the $10 million investment. And likewise, if we fail right off the bat from the investment, then we would lose our investment amount. And then the not invest is do nothing. So that's part A. Part B, what I'm going to do now is actually, I think what we'll do is simplify this, and we will get rid of this tree, and we'll clear it. And the beauty of that is I'm going to go through part B. So this is part B. And so I'm going to draw some of these trees a little smaller and abbreviated. So we have a 0.6, 0.4, and this is going to be 40 minus 5. And then emanating. Notice I'm drawing backwards because it's easier to draw these things. It's a little trick I learned. Let's see, 0.5, that's my success branch. My fail branch, 0.5. minus 10. So all I'm doing is redrawing these so we can solve it. I'm going to let I be investment, and then our decision node, if we not invest, then it's going to be 0. And so for this, I'm going to say I, and I'm going to put a prime here saying it's not invest. So as I roll back the tree, the first thing I come to is an uncertainty, and once again we need to do the expectation operator, which is the expected value. So the expected value of this node is going to be 0.6 times 40 plus 0.4 times minus 5. If you go through that mathematics, you should get 24 minus 2, which is going to be 22. So now this whole thing can actually be collapsed into, I'm going to redraw it down here. So our tree is going to look similar. In this case, since it's a little smaller, I can draw it probably just as easy. So investment decision, I have my chance of success, 0.5. So this is my success branch. And you can put that up here if it helps you think through it. Success, fail, success and fail, 0.5. And now we have the expected value 22. So this little subtree collapses to 22 is the expected value. And this is going to be a minus 10. Then my not invest path or branch is still that way, still 0. So once again, as I start the rollback, I start the far right hand part of the tree and I roll back to the first node I hit, which is an uncertainty, and I need to do the expectation again. And so it's 0.5 times 22 plus 0.5 times minus 10. And if you go through that computation, you'll get 11 minus 5, which is going to be 6. So once again, as I show what's going on in my rollback method, in this case, my tree has been reduced quite a bit. So now I have an investment. And the expectation of this little subtree, we just did it over here, was a value of 6. Make it bigger here so you can read it, 6. And the corresponding do nothing or not invest is 0. So now my tree has reduced even further just to the two decision alternatives. And as I roll back my tree once again, I come to a square, which is my decision, and a decision is a choice. So unlike a circle, an uncertainty, which is an expectation, the decision is a choice. So in this case, I can choose. Would I rather have $6 million or 0? Not a very hard choice. I would rather have 6. So in this case, the expected value, I would go this way. The arrow represents where I'm going to go and not go down that path. So the expected value of the investment decision is $6 million. The expected value of the not invest is 0. So I would say, therefore, invest. That's part C.